Greetings of day to all of you. Today is Tuesday, 3rd January 2023. This is the first lecture that I am going to deliver in the month of, in the new year 2023. First lecture of 2023, and overall it is lecture number 3. So in today's lecture, I am going to discuss with you dynamics of electric drives. I'll write here dynamics of electric drives. Okay, in dynamics of electric drives, let's consider a simple block diagram or schematic diagram whereby I am showing the prime mover, which is motor. It may be a DC motor or an AC motor whose shaft is coupled to the shaft of a mechanical load. This is the load. Okay. Now the motor is, for example, developing a torque T, which causes the motor and its driven load to run at a speed of omega m, say in clockwise direction. The torque which is exerted by the load is in the opposite direction to the torque developed by the motor. This is the load torque, which is in anti-clockwise or counterclockwise direction, and this is the torque developed by the motor, which is in the clockwise direction. So what this torque has to do, the motor has to develop a torque at least equal to or greater than the load torque to keep the motor and its driven load rotating in clockwise direction at a speed, say omega m. Now if you write electromechanical equation for this motor load arrangement, the equation is like this: T minus TL, that is motor torque minus load torque, is equal to d by dt of J into Wm or omega m, where what is J? J is moment of inertia of the motor and load. The entire system has a moment of inertia J. Okay, so we can write T minus TL is equal to, if you differentiate this, so this will be J d omega m by dt plus omega m dj by dt. Now what is J? J is the inertia, and since the inertia of the system is constant, so therefore dj by dt is constant, since the system has a constant inertia. Okay, so therefore dj by dt will be equal to 0, because the differentiation of j, which is a constant term, is 0. So therefore this whole term will be equal to 0. So therefore T minus TL is simply equal to J d omega m by dt. Right. We can also write it as T equal to, that's the torque developed by, electromagnetic torque developed by motor, is equal to load torque plus J d omega m by dt. Where what is TL and what is J d omega m by dt? TL is the load torque. This is load torque, and J d omega m by dt is called torque due to inertia, load inertia, or we call it inertial torque. And let me tell you that this term J d omega m by dt, which is also called inertial torque, it will be present only during the acceleration of the system and during the deceleration or braking of the system. When the motor is connected to the source initially, the whole system starts from zero, from standstill. The motor and its driven load is at standstill. And then the system starts accelerating. During the accelerating, the torque to be developed by the motor should be equal to load torque plus torque due to inertia or inertial torque. So therefore T should be equal to TL plus J d omega m by dt. That will cause acceleration of the motor and its driven load unless the load reaches its steady state speed, and it runs at a constant steady state speed omega m. So therefore I will write at steady state when the system reaches steady state, omega m is constant. That means the system runs at constant speed. Initially it was accelerating. During acceleration the speed was increasing, and finally it reaches the rated speed and runs at constant speed omega m. So therefore, what is the differential of d omega m by dt? Since omega m at steady state is constant, so this is equal to 0. So therefore at steady state the torque developed by motor should be simply equal to load torque, because this term is 0, right? So therefore it is very much obvious that when you start the motor and it's driven load, due to the inertia there is inertial torque, the motor accelerates, the motor should develop sufficient torque which is equal to load torque plus inertial torque to keep the system into motion, or to accelerate the system. When the system accelerates, T is given by TL plus J d omega m by dt, and once the system reaches its steady state condition and the load runs at steady state speed, constant speed omega m, then the motor has to develop a small amount of torque which is equal to TL. So during starting, the torque developed by motor is large. It is TL plus J d omega m by dt, which causes acceleration of the system. And finally at steady state, the motor has to develop a small torque which is equal to load torque TL. So therefore, if the system is of very high inertia, if your load is of very high inertia, the motor at the beginning has to develop a very large torque which is equal to TL plus J d omega m by dt. And if you have to accelerate the motor very quickly, then this T should be very, very large, and you have to maintain this T during the entire acceleration of the system, so that the system accelerates quickly and it reaches the steady state speed, beyond which T is equal to TL. Similarly, when the motor is braked, I mean it is decelerated, when you apply brake on the motor to brake it, to decrease the speed and to stop the motion of the load, what happens? This d omega m by dt, that is the inertial torque, it changes its sign. It becomes minus. During acceleration it is plus, during deceleration it is minus. Now this negative inertial torque means that it is assisting motor in running at the speed omega m. You are applying brake on the motor and it's slowed, so it is decelerating, but this term is helping. It is the whatever kinetic energy is there stored in the motor and its driven load, it is releasing that kinetic energy and transferring that kinetic energy to the system and keeps the system rotating for some time at speed omega m. However, what happens? The system will not keep running on this constant speed omega m. It will decelerate, but it will decelerate slowly depending upon the moment of inertia of the load, and finally it will come to a standstill. Now if you want to brake the motor quickly, then this braking torque should be very, very large, okay, because this inertial torque is helping the motor in running the same speed, running in the same direction at the same speed. So you have to apply a large braking torque. Now the question is, as far as this inertial torque is concerned, can we use it somewhere? I mean, this inertial torque J d omega m by dt, let me tell you that it is very useful in certain types of applications. One of the application is pressing machine. In a pressing machine, what happens? The machine, moves down and it presses a load, okay? When it tries to press some load, at that time the load is applied on the motor, and when pressing phenomenon is over, okay, the motor is not pressing the load, then motor runs at no load or at light load. So if you see, in a pressing machine, the motor and its driven load, or the motor runs at no load or light load for most of the time, and only during the pressing phenomenon or pressing process it runs at full load. So when pressing phenomenon takes place, or when pressing is done by the motor, at that time this inertial torque will be very helpful. So let me try to elaborate what I mean to say. Let us suppose this is the motor and this is the load. The load may be pressing machine. what we do is that this pressing machine is coupled to a large flywheel. This is flywheel. What happens when the motor is started? It accelerates the load. When the load accelerates, the motor accelerates, but pressing is not done. So the motor runs at no load or at light load, and it causes the flywheel also to accelerate. During acceleration, the energy is stored in the flywheel. Okay, and the inertial torque is J d omega m by dt. What happens is that the flywheel is accelerating, its speed is increasing, and it stores the kinetic energy. The kinetic energy stored in the flywheel is half of J into omega m square. So kinetic energy gets stored in the flywheel, and this is the inertial torque. Okay, so then the motor runs at steady state, say at rated speed. Then at that time, J d omega m by dt becomes equal to 0. But kinetic energy is already stored in the flywheel and it is running at a steady speed. Now let us suppose the pressing process takes place. The machine presses. Okay, it moves down and it makes a press. When this pressing phenomenon takes place, at that time, what happens to the motor? Motor applies torque, because for pressing phenomenon, certain amount of torque is required. So it applies the torque for doing the pressing phenomenon, and simultaneously what happens, the motor, while doing this pressing process, it decelerates. And when it decelerates, what happens to this inertial torque? I told you earlier also, when the motor decelerates, the inertial torque becomes negative. So therefore the torque to be developed by motor should be equal to load torque minus J d omega m by dt. It will not be plus. It will be plus during the acceleration process. And during the deceleration, when the pressing is done and when motor decelerates, it will change its sign, minus. Minus means the flywheel is now, whatever kinetic energy it had stored during acceleration, it is now releasing that kinetic energy and supplying that kinetic energy to the load. So therefore this inertial torque becomes negative and it adds to this motor torque. So if you take this term towards left hand side, so this will become T plus J d omega m by dt equal to TL. So you don't have now T equal to TL, because during the pressing phenomenon, a large amount of load torque is required. So what is your equation? It's not T equal to TL, it is T plus J d omega m by dt equal to TL. So therefore this inertial torque, which changes its sign, it adds to the motor developed torque and it becomes equal to load torque. So therefore this has the impact on the rating of the motor. You require a motor of smaller rating for developing a large torque which is equal to TL during the pressing phenomenon. Assume this flywheel is not connected to your load. When flywheel is not there, then in that case T has to be equal to TL during the pressing phenomenon. And since during the pressing phenomenon the load torque requirement is very large and the motor also requires to develop a very large torque, the size and rating of the motor required is very large. However, because of this flywheel, what happens during the pressing phenomenon, when the motor presses the load, when the machine presses the load, then T is equal to TL minus J d omega m by dt, where J d omega m dt becomes negative. It's the inertial torque due to flywheel. Flywheel is releasing the kinetic energy, supplying kinetic energy to the motor. So motor torque plus inertial torque becomes equal to load torque. So therefore the torque to be developed by motor is not equal to load torque. It is less than load torque, because this torque adds to motor torque and the sum of the two becomes equal to load torque. So therefore this inertial torque helps us in reducing the rating of the motor. So therefore in this case, when you use the flywheel during the pressing phenomenon, flywheel supplies the inertial torque to the motor. So the T plus J d omega m by dt becomes equal to TL. You require a motor of smaller rating. So smaller rating motor is required. If flywheel was not used and we were not able to use this inertial torque, then T would have been equal to TL and a motor of large rating was required. So this is how we can make use of this inertial torque for reducing the rating of the motor. Fine. After this, I will discuss with you speed torque, torque speed convention of an electric drive, torque speed convention, and four quadrant operation. And four quadrant operation. Four quadrant means 4Q operation of an electric drive. My dear students, all of you must have studied a course on electrical machines. When you were taught electric machines by your machines teacher, and when the machines teacher was discussing with you about torque speed characteristics of any motor, whether it is a DC motor or AC motor, for electric machines, electric motors or electric machines, generally what we do, along the x-axis we take the speed. Speed is plotted along x-axis and torque is plotted along y-axis. So for example, let's take an induction motor. The torque speed characteristic of an induction motor is like this. Speed is plotted along x-axis and torque is plotted along y-axis. Similarly, the torque speed characteristic of DC series motor is something like this. However, in electric drives, we will not be using this convention. We will be using the reverse convention. Reverse convention means the torque will be plotted along x-axis and speed along y-axis. So for electric drives, the speed torque or torque speed convention is like this. Along the x-axis, we will be plotting torque, and along the y-axis, we will be plotting the speed. So this is just reverse to the convention of electric motors. For electric motors, speed is plotted along x-axis and torque along y-axis, but for electric drives, torque is plotted along x-axis and speed along y-axis. The reason being that to start an electric drive, you need certain amount of torque, and only when that torque is available or it is produced by the drive, then only the drive starts rotating at certain speed. So to get the drive rotating at speed, you need certain amount of torque. So that is why the torque is plotted along x-axis and speed is plotted along y-axis. Regarding the four quadrant operation of an electric drive, four quadrant operation can be understood in torque speed plane, and it is required for reversible operation of the motor or for reversible motors or reversible drives. So it is something like this. This is the torque, positive torque, this is the negative torque, this is the positive speed, and this is the negative speed. This is origin 0. Now you can see if your electric drive is operating in, this is first quadrant, this is second quadrant, this is third quadrant, and this is fourth quadrant. If electrical drive is operating in first quadrant, in the first quadrant you can see, let us take this torque as positive and the speed along y-axis as positive. So the torque is positive, it is greater than 0. Speed is also positive, omega m is positive. What is power? Power is omega into t, omega m into t. Since omega m, that speed is greater than 0, it is positive. Torque is also greater than 0, it is also positive. So power is also greater than 0, power is positive. Positive power means that the power is supplied by electric supply to the motor and its driven load. And the motor converts this electrical energy into mechanical energy and starts running the motor. Say for example, it develops torque in clockwise direction, for example, and the motor runs in the clockwise direction, omega m. So this mode is called forward motoring mode. I will write here forward motoring mode. FMM means forward motoring mode. So our motor and the drive is running in the forward motoring mode. Okay. Now if you want to brake the motor, you want to brake the drive, you want to stop it. Okay. Speed is still in the same direction. It is in the clockwise direction. But you want to apply a braking torque. You want to slow it down. You want to stop it. So what should be the direction of torque? Torque should be in counterclockwise direction so that it slows down the motor, and finally brings it to standstill, stops it. So therefore, what is the convention now? In the second quadrant, speed is positive, greater than 0. You can see it's in the same direction as in first quadrant, but torque becomes less than 0. Torque is in the counterclockwise direction, whereas here torque was in the clockwise direction. So torque is less than 0. So what is power? Power is omega m into T. Since omega m is positive but torque is negative, so power is also negative. Now negative power means the drive is not taking power from this electrical supply. It is supplying power back to the source. And in the process, the direction of torque reverses. It acts as a braking torque, and it slows down the drive, or it may even stop the drive. This mode is called forward braking mode. I will write here forward braking mode. FBM. This is also called forward regeneration mode. Forward regeneration mode. FRM. Why is it called regeneration? Because the machine which was acting as motor in the first quadrant, the same machine will act as a generator. It will generate the electrical energy, it will convert braking energy into electrical energy and supply that energy back to the source. And while doing that, the direction of torque reverses and it acts as a braking torque and it brakes the motor. So this is forward regeneration mode or forward braking mode. Now, if you want to run the motor in the anti-clockwise direction, for example, in the forward motoring mode, motor was running in the clockwise direction. If you want to run the motor in the anti-clockwise direction, the torque developed should also be in the anti-clockwise direction, counterclockwise direction, so that torque is in this direction, speed is in this direction, and the motor runs in the reverse direction. Okay. So in this case, what is omega m? Omega m is less than 0, it is negative. Torque is also negative. So what is power? Power being the product of speed and torque. Since both are negative, minus into minus is plus. So power is greater than 0. That means power is positive. Positive power means that your machine is running as a motor. It is drawing electrical energy from the source, converting that electrical energy into mechanical energy, but it is running in the reverse direction. In the first quadrant, it was running in the forward direction like this. In the third quadrant, it is running in the reverse direction like this. Okay, so this mode is called reverse motoring mode. Reverse motoring mode. That means if your drive is operating in third quadrant, so it is operating in reverse motoring mode, RMM. Finally, now if you want to brake the motor and it's driven, you want to brake the drive, the direction of torque should reverse. I mean, if the speed is in counterclockwise direction as in quadrant 3, but torque should reverse its direction. It should be in clockwise direction so that it brakes the motor, stops, slows it down, and finally stops. So in this case, what is speed? Speed is negative, but torque, you can see it has become now positive. So P, power being the product of speed and torque, one of them is negative, so power is also negative. Negative power means that your machine, which was acting as a motor in third quadrant, it will act as a generator. It will take the braking energy of motor and its driven load, convert that braking energy into electrical energy and supply that energy back to the source. So that means your machine is not operating in the motoring mode, it is operating in the generation mode or generating mode. And in the generating mode, the direction of torque reverses. It opposes the motion of the motor and the drive finally slows down and it may stop. So this mode is called a reverse regeneration mode or reverse braking mode. Reverse braking mode, RBM, or it is also called reverse regeneration mode. Reverse regeneration mode, RRM. So this is the 4-quadrant operation of an electric drive. You can operate your electric drive in forward motoring mode or in the reverse motoring mode. While going from forward motoring mode to reverse motoring mode, you have to go via forward regeneration mode, brake the motor first, stop it. While braking the motor, the braking energy should not be wasted, it should be supplied back to the source. So that happens in the quadrant 2, which is the forward regeneration mode. Similarly, if you want to go from reverse motoring mode to forward motoring mode, you have to go via quadrant 4, which is the reverse regeneration mode, where the machine acts as a generator, supplies energy back to the source, and while doing that, the direction of torque reverses, it breaks the motor. So while going from, I repeat, while going from forward motoring mode to reverse motoring mode, you have to go via forward regeneration mode. Similarly, while going from reverse motoring mode to forward motoring mode, we can go via reverse regeneration mode. In other words, while going from quadrant 1 to quadrant 3, we can go from quadrant 1 to quadrant 3 via quadrant 2. Similarly, we can go from quadrant 3 to quadrant 1 via quadrant 4. Let me give practical example of 4-quadrant operation of an electric drive. Practical example. Practical example of 4-quadrant operation. So it is something like this. I will again draw the torque speed plane. This is torque, positive torque, this is negative torque, this is positive speed, and this is negative speed minus omega m. Let us suppose we have a hoist which has to lift a certain amount of load from, say, lower level to higher level. This is the load. It has to lift it through certain height, and this is called counterweight. This is CW. I will write here CW means counterweight. Now in this is your drive is operating in quadrant 1. The objective is to lift this load, say, over certain height. There is some mechanical load in this cage. This is cage. There is some load in this cage, and we want to lift it to, say, 10th floor of the house or 20th floor of the house. We are using this hoist for that purpose. Okay. On the other side of hoist, we have counterweight. The weight of the load in the cage is more than the weight of the counterweight. Okay. So obviously this weight will not rise. It will not move upwards, because the weight of the load here, which is in this cage, is greater than weight of the counterweight. So obviously the torque, load torque, will be like this. Now in order to lift the load towards certain height, it should go up like this. So therefore the motor, obviously this pulley is connected to a motor. The motor should operate in the first quadrant. It should draw power from the source, convert that electrical power into mechanical power, and develop a torque T, which is equal to load torque. And obviously it will cause the motion of the load in this direction, say in counterclockwise direction. The pulley will move in the counterclockwise direction, and it will lift the load. Load will go up. Okay. So this is how you operate your drive in the first quadrant. What will happen in second quadrant? In the second quadrant, the situation is like this. This is again pulley, and this is counterweight. And let us suppose the load is, the cage is now, at the 10th floor, you have taken the load out of the cage, and the cage is now empty. You have an empty cage. I will write here empty cage. Now since cage is empty, okay, the weight of the counterweight is more than the weight of the cage. So the counterweight is more than the weight of the cage. So obviously this counterweight will pull it up, okay, and it will start moving in this direction. So this is the direction of load torque. But we don't want this cage to move up at a very high speed. We want it to move up steadily at some steady speed. So therefore what will happen, the machine which was acting, which was developing positive torque here, it will develop a negative torque. The positive torque was, say, in this direction, and this is the, by convention, this is the negative torque. But what is the motion? Motion is same. This is the motion. The motion is, bottom to top. Here also motion is bottom to top. But we don't have any weight in the cage. The cage is empty. So we want that this cage should not move very fast. It should move slowly. So therefore, what will happen when it moves up? The motor should operate as a generator. As a generator, the braking energy, it will convert into electrical energy and supply that energy back to the source. And while doing that, the torque developed by generator is opposite to torque developed in the motoring mode. So it is developing the torque which is opposing the motion of the, this pulley, or motion of the motor, or motion of the, so no doubt the cage is moving up. Now since this is the opposing torque, it opposes the, motion, and it slows down. So it is moving up slowly. So this is how you can make it do in second quadrant. In second quadrant, this is the forward regeneration mode. This is forward motoring mode. This is forward braking mode, or forward regeneration mode. What about third quadrant? This is the third quadrant. In the third quadrant, the situation is now like this. This is again counterweight. And this is the cage. Sorry, this is the cage. This is empty cage. I will write again empty cage. The direction of motion of motor is like this, right? Sorry, it has reached this. The direction of torque is TL, because weight of counterweight is more than weight of empty cage. So torque will be in this direction. But now we want this cage, say it is at 20th floor. We want it again back to ground floor. So it has to be moved down. So in order to move it down, in the first quadrant, the cage was moved upwards. So direction of torque was, direction of speed was like this. Now in the third quadrant, once it has unloaded, all load has been taken out of this empty cage and it has reached the top level. Now we want to get it back to the ground floor so that it can take load again back up, so that it can be loaded again and load can be taken up again. So it has to be brought down. Okay, but what is the weight of the counterweight? Weight of the counterweight is more than weight of the empty cage. So obviously this cage will not come down of its own, because it is being pulled in this direction. So therefore the motor has to develop a negative torque which is opposite to the torque of the load TL, and motion also has to be opposite. In the forward motoring mode, the direction of torque was positive like this, speed was also positive. Now here direction of torque is negative, speed is also negative, and this cage will start moving down till it reaches the ground floor. So it will move down like this. So this is reverse motoring mode. Why it is reverse motoring mode? Because the direction of motion of load is opposite. It is moving top to bottom. Here it was moving bottom to top, ground floor to top floor. Here it is moving top floor to ground floor. Okay. Let us quickly go to, this is in quadrant 3. What happens in quadrant 4? In the quadrant 4, the situation is something like this. This is the counterweight, and this is the cage, loaded cage. I will write here, this is not empty cage, this is loaded cage. Let us suppose the weight of load be greater than weight of counterweight. So now you have taken it to top floor and you have put some load. Now in the first case, you had to take some load upwards. Now in this case, you have to take load downwards. So when you put the load into the cage, the weight of the load is much greater than weight of the counterweight. What will happen? The load will develop a torque load, this is the load torque downwards, and the, you know, this load will move at a very high speed downwards in order to avoid dangerously high speed, so that it does not come down very quickly at a very high speed and it does not strike the ground at a very high speed. In order that this load comes down slowly at a steady speed, what should happen? The machine should operate as a generator. Since it is moving down, it is moving down at a very high speed, so motor overspeeds. It is operating as a generator. The machine which was operating as a motor in this quadrant 3, now it is operating as a generator, and as a generator it is developing torque in the reverse direction. As motor, this is the direction of torque, clockwise. As generator, the direction of torque is anti-clockwise. So this is the direction of torque. This torque acts as a braking torque. No doubt the load will come down, but it will come down slowly. Why? Because this electromagnetic torque developed by machine opposes the load torque, and it moves down slowly till it rests at the ground floor. So this is how we operate it in the fourth quadrant. In the fourth quadrant, our system is operating in reverse braking mode, RBM, or you can also call it reverse regeneration mode, RRM. So this practically shows that when you take load, mechanical load, from ground floor to some height, or when you move down the load from height to the ground floor, so, and or you have to move the empty cage upwards, or you have to move the empty cage downwards. This is how 4-quadrant operation takes place. Quadrant 1, forward motoring mode. Quadrant 2, forward braking or forward regeneration mode. Quadrant 3, reverse motoring mode. And Quadrant 4, reverse regeneration or reverse braking mode. So this practically shows the 4-quadrant operation of an electric drive. So with this, I will conclude today's lecture. We will have more discussions on dynamics of electric drives in next lecture. Thank you.